Okay. Hi, hello. I'm going to go ahead and start getting into things. Welcome to section. It's lovely to have you all. So if you can, go ahead and scan this QR code and fill out the little attendance survey. So attendance in section is not mandatory, but I like to use the metaphor that, like, in chemistry, I am the mother duck, and you are all my little Orgo duckling babies. And I like to keep track of the little duckling babies and make sure none of them, like, fall off a cliff. So I do take attendance and kind of monitor it, but it doesn't affect your grade. For this survey, it's going to have some just like intro questions, and we're going to do introductions as part of the first section today. So the things that you write down on that, you're probably going to be like sharing in a few minutes with us as a group. So welcome in people that just came in. And then if you can scan this QR code, I'll also have it up a little bit later for you to scan for people who come up a little bit late. Cool. So, a little outline of today, or I did think I cut off someone who was just trying to take the picture of it, but we'll come back to it if you don't get it, okay? So we're going to start off doing introduction things of just like, hi, who are you, why are you here, what's going on? Then I'll give a bunch of information that's really boring, which is like course logistics of how everything's going to work, because Logan only had about 10 minutes in lecture to spend on things, and like there is some like detail to the stuff that you need to know in terms of exam procedures, in terms of homework submissions and everything. Then I'll talk about some of the resources available to you and some advice with kind of like building your study schedule. And then we'll switch over to kind of real section things. So I guess first off, welcome, brave souls. You all have made, I think that you have made a bold decision by doing summer organic chemistry and like trying to do Orgo in 7 weeks. Like it is a kind of intense experience. But also, like, we are here to support you. For context, the first organic chemistry class that I did at Harvard, I started off by taking Chem 30, which is, like, the honors second semester OChem 2 class, because I was a precocious little high schooler, and I took organic chemistry in high school. And so I said, oh, I can do organic chemistry at Harvard. And they did put on the door, abandon hope, all ye who enter here. And that was the vibe of the class. Like, it was very, very intense. I don't want that vibe for this class. Like, it's very much like we're here to learn it together, and I'm going to do everything I can to help kind of support y'all. But it's not a, like, 60% of you have to fail, otherwise I haven't done my job. Yes, but the vibe of the summer organic chemistry is very, like, boot camp. It's like y'all are probably going to be doing, like, 6+ hours, not every day, but, like, if you have lab and lecture, you're already having, like, 7 hours of organic chemistry. And then just the homework, like you've seen, the problem set. I'm so sorry. Like, I'll talk a bit more about the details. It's kind of the only way it works to do it in the summer. And we've tried it, doing it without the practice problems being assigned, and more students fail. So yes, Orgo has a reputation, and whenever you take organic chemistry, it's going to kind of take over your life a little bit. The nice thing about doing it in the summer is you have fewer things competing for your time than like a normal semester generally. Now, I think a lot of times students walk into organic chemistry and they're like, I don't know if I can do this. Like, this is a kind of make or break class for like pre-med or whatever. If you are here in this room taking this class, you can do organic chemistry. Like, there is not a like doubt in my mind of can you learn it. A lot of it has to do with like contextual things of like, do you have to take another class on top of this one? Because that's really hard to balance and juggle with the intense summer semester. Are you working on top of this? Or are you doing an internship or a lab thing? Like, if you don't have enough time, I think that's where students get in trouble. It's not really about like your inherent ability in organic chemistry. The other thing is, Logan's great. I really like Logan. I have taken organic chemistry now at a few different universities. I have tutored organic chemistry for students at like over 20 other schools. And then I did chemistry major here at Harvard. The best OChem professor I've found is Logan, which I know the bar is low for like our organic chemistry professors. They are not typically the most charismatic. But, like, I think Logan does a really, really good job of, like, being thoughtful of how to present it, making lectures a little bit more engaging. If I had to, like, poof all organic chemistry away from my mind and take organic chemistry from scratch, I'd take it with Logan. So I'm glad that he's here and working with us. Um, cool. So we are going to start off with some introductions. So for introductions, I have some questions for you, which is one, who are you? Like name, preferred noun, pronouns. Where are you from? Where are you at in your education? So I think Logan mentioned this a little bit, but one of the cool things about this course to me is it has learners at various different stages in their education all in the same class. So we have some high school students who are here doing it with the secondary school program. We have a majority of the class is Harvard College undergrad, so that's kind of the main body of the class. And we also have students through the extension school. So either students who are taking this as like a one-off class who are at another university, or students who are doing the post-baccalaureate program where, let's say they got their major in government, but then they decide they want to go to medical school and they're doing all the pre-med requirements. So it's an interesting kind of mix of people at various different points in their education, which I think makes the class interesting and cool. And then last thing, why are you taking this class? So I have a lot of enthusiasm, but I'm not precious about organic chemistry. Like, I don't love organic chemistry. I like teaching. And, like, I'm as enthusiastic about, like, calculus or, like, Gen Chem. Like, it is what it is. So a very valid answer to why are you here is pre-med. I have to take this for a degree. Blah. That's totally fine. So let's start. Can we start with you in the back, and then we're going to, like, snake down and around. And as y'all are talking, I'm going to try to check you off on the attendance thing just to, like, try to match faces with names. So you'll see me probably, like, scramble, and then I'll be like, ah. But why don't you start us off?
Okay. Hi, my name is Sophia.
Sophia.
Sophia Ramirez, in case you like not know who it is.
Work.
I'm from San Antonio, Texas, and I'm a rising sophomore at the college, and I'm pre-med. Before I take the class.
I just have this sound loaded up, so I want you to know, being from Texas, that right now where we are,
Oh.
no. So, welcome.
My name is Marcos Garcia, pronouns are he, him. I'm from Detroit, Michigan. I'm a Harvard College sophomore now. And I'm taking OChem because I'm pre-med.
Work.
I like chemistry, and it's required for my position.
Work. What's the concentration?
MCD.
Nice. Work.
Hi, I'm Lila. I use she, her pronouns. I'm from Omaha, Nebraska. I'm a rising sophomore, and I take this class from pre-med.
Work.
And I'm Matska. I use she, her pronouns. I'm from Syria, and I also studied and lived in Canada for 2 years. I'm a rising sophomore at the college. I'm taking the class because I'm pre-med. I'm also chemistry trained for organic chemistry.
Oh, work. Also, there were like 2 Canadians or 2 people from Canada in the 8:30 a.m. You said you're not from Canada, but
I
just
just live there.
there is a Canada cohort around, so find the peoples. Work.
Hi, I'm Sarah. I'm from Texas, and I'm currently a rising sophomore at Harvard College, and then I'm taking the class for pre-med.
Work.
I'm James. I took the Keaton series. I grew up in Boston, but I lived in Houston for 8 years, and I lived in Canada for 5 years. So,
I mean,
um,
do I play it one last time? Did you?
I actually just graduated, but I'm taking this class because I just graduated from Harvard. I'm taking this class because I decided like junior spring to do pre-med,
Work.
and I've done everything but translating. So.
Work. Very nice. Well, and also they just couldn't keep you away. You said I need to get more Harvard. Yeah. Work.
Hey guys, I'm Dylan. I use he, him pronouns. I'm from Boston, so from around here. I'm a rising senior in high school, and I'm taking this class because I like chemistry.
King Dong. And again, you're in good company as high schooler taking organic chemistry because I did the exact same thing. Yeah, it's a vibe.
I'm Ryan. I use the she, her pronouns. I'm from Utah, Massachusetts, a half an hour away from here.
Oh, work.
I'm a rising sophomore at the college, and I'm also pre-med.
Cool.
Hi everyone, I'm Evan. I use the she, her pronouns, and I'm also a rising sophomore here at the college. I'm not pre-med, but I'm doing biomedical engineering, so it's
Okay, cool.
good time.
Very nice. Work.
use she, her pronouns. I'm from just outside of Boston. I'm a rising sophomore at college, and I'm pre-med.
Very nice.
Hi, I'm Maya. I use she, her pronouns. I'm also from Texas. I did this.
Thank you. Wow, the Texas coalition. Y'all certainly outnumber the Canada coalition at this point, so watch out.
I got a brown, but they canceled some of them, so I'm here.
Sad.
And I'm doing it because I'm here now.
Word.
I'm Nari. I use she, her pronouns. I'm a rising sophomore at Harvard, and in this office, I'm pre-med.
Word. Welcome.
Hi, I'm Katie. I use she, her pronouns. I'm from Worcester, Massachusetts, and I'm going to be a junior at Brown. And like she said, they canceled it. So.
Wait, did y'all like know each other going in? Like y'all were both? Oh, okay. Work. There might be more. We'll see.
It's like brown refugees.
Oh, yeah. Okay. So we have all the Massachusetts natives. We have the Texas cohort, the Canada cohort, and we have the brown
We
refugees.
need to form cliques now.
Yeah.
Like,
Yes. Ding dong. And then let's sneak around over here. Hi.
My name is Rachel. You can call me whatever you like. And I'm from China. I take this class because I think organic chemistry is beautiful.
Work.
I'm Hannah. She, her pronouns. I'm from Colorado. And I'm a rising sophomore at Harvard. And I'm taking this class because pre-med, and then I don't want to take it again basketball season.
No, that's very valid. Mark.
I'm Cameron. I use he, him pronouns. I'm from Richmond, Virginia. I'm also a rising sophomore here at the college. I'm taking this class because I'm pre-med. It's also applied for my concentration.
Work. And Cameron or Cam?
Campbell.
Okay. And then there is another Cam in the class. So what's your last name?
Walker.
Walker. There's a Cam Wilson. So another Cam W. Dang. Okay. Nice to meet you.
My name is Nahal. He, him pronouns. I'm from Toronto, Canada. I'm a sophomore here. I'm a rising sophomore here, and I'm taking this class for pre-med.
Very nice.
Steven from Connecticut, also rising sophomore. And it's pre-med and maybe concentration and probably also partly the fun and self-torture categories on the screen.
Ding dong. Ding dong. We love to see it.
I'm the other Cam.
Whoa. Okay. Plot twist.
I use he and pronouns. I'm a rising sophomore in Harvard College and good for pre-med and concentration regardless.
Work. I am trying to find you on the list, and then it just disappeared. I literally just read your name.
I mean, I'll go home.
Cam.
Yeah.
There we go. And then Cameron. Cool. Is there a Dina here? Is there a Jenny here? And then is there a Sophia? You're Sophia. I didn't check your name. Thank you. And then I think last one is Smart. Work. Cool. So, time for me to do my introduction. Because I made the PowerPoint, I get to have a slide. So my name's Colton. I'm non-binary. I take any all pronouns. I'm a Virgo. I'm from Athens, Georgia, where I live during most of the year, and then I come back up for the summers. I did my undergrad at Harvard. I was in the social class of 2020, but then actually graduated in 2021. And they weren't doing physical graduations at the time, so they sent me a digital degree. So now I have a file on my computer that says my Harvard degree, I guess, .jpeg. And so, I did all that work for that.
Can you go to like the register or something and get a physical one?
Yes, and we ended up getting it like a year or two later. But again, that file will always live on. At the college, I was in Elliott House my sophomore year, and then I transferred to Courier House, which is, for the non-Harvard folks, uncommon to transfer to the Quad because it's further away. And also, it has a retirement home vibe. Like, it has, like, this fountain and then Courier House. I want to retire. I want rest. I want peace. The river is too active. Like, I need to calm down after the end of the day. Then when I was here at Harvard, I did a bunch of musical theater. So these are some production pictures from shows I worked on. I primarily was conductor and music director, so I worked in the kind of like tech theater side of things rather than like on stage. And so it's a production of Chicago. This was like an artsy interpretation of Shakespeare's The Tempest that we performed in a building that was like demolished 3 days after we left, like when they were renovating Adams Art House space. But I am currently taking classes at the University of Georgia here, which is like 10 minutes from where I live. And kind of just for fun. Like I finished my degree and then I started working as like a math science tutor for a company in my area, and then I left and started my own business, and then I was like, I miss school. And Harvard doesn't have a biochem major. Like it has molecular cellular biology, it has chemistry, but I wanted biochem. And so I like dual enrolled and I took like the junior and senior level sequence of biochem at the University of Georgia to see kind of a traditional sequence. Like I wanted to know what was up with hemoglobin. I wanted to know what was up with metabolism. And then I was also like, I miss math. And so now I'm like one class away from like a math degree. And so like I have thoughts of like maybe we will get some of these, but we're really just vibing and taking classes and like learning. I have a picture of my sweet dad over here. My dad's Stan. I'm a caretaker for him. So I include that also because sometimes I just like have to go out and take a call related to his stuff. So I just like to give a heads up. I also have a little radio tower by him because when he was working, he owned and ran 4 radio stations. So now I run 4 radio stations. So again, lots of different hats that we are wearing. And then up top is Daisy, my sweet dog, who I've left in Georgia, staying with a friend. So if you have pets or if you have pets that you miss, show me pictures of your pets, and then I'll like probably well up and do an aw. Yeah, and this is my 7th year with the class. I really like it. I started off just like doing like 1 section, and then I did 2 sections, and then I said 2 sections of DF, and then here we are. But I really like coming back up to Boston and Harvard's campus in the summer, and like it's always been such a positive experience working on S17, so here we are. Okay, so now we go to much more boring things. So I'm going to try to get through this as quickly as possible, but there is just a lot of detail to go through of like the perfunctory things of how the course works. So we're going to start off with things to turn in for this class. The first one is already assigned, the lecture quizzes. These are short 10-question quizzes that reinforce material from lecture. You have 3 attempts at it, and we take your highest attempt. After your submission, it should tell you which questions you got incorrect so that you'll know that and can just change your answers for those. They are graded on accuracy, and because you have 3 attempts, there are no dropped quizzes. So the only time students get in trouble are when they forget to do the quiz. So don't forget. They are due essentially like Tuesday's lectures ones, the quiz is due Wednesday night, and then Thursday lecture it's due Friday night, and that's on the course schedule as well. Then we have problem sets. So again, I'm so sorry. Like this is a lot and it's tough. You do have the answers to, I guess, 38 pages of it. So hopefully that should make it a little bit easier. The problem set's divided into the skill builder problems, which you have the answers to, which for a normal class would be practice problems. And then the last 8 to 10 questions are challenge problems. Challenge problems, you do not have the answer, hence it's a challenge. And then also they're exam level problems. So it gives you an idea of kind of the level of things that you'd be asked for. Now, the skill builders, it's really up to you to like do them in an effective way. Because you can straight up just copy what's on like the answer key, but then you're not doing any of like the learning. But then other people try to go to the other extreme and they try to do like, I'm not even gonna look at the answer key, I'm just gonna like go in, I'm gonna learn all the organic chemistry, and you just simply don't have time for that. Like to do 47 pages from scratch, like not looking at the answer key, you don't have time for skill builders to spend 45 minutes struggling on one of those intro pages in the first like 36. So use the answer key as a helpful tool for you. Engage, try to learn the material, and if you don't know something, look at the answer key, and then if it still doesn't make sense, ask. Okay, so Problem sets are due Monday via Gradescope, digital, just export it and like upload it to Gradescope. Make sure it has the right number of pages, and I like tried to put it in like bold on the first page, exactly 47 pages, all the things. It just makes it really hard to grade in Gradescope without that. But also, even though problem sets are pretty long and tedious, they should not be super stressful because they're not graded on accuracy. They're graded on effort and completion. So with that, if it looks like you have done the whole page, you've given it an honest attempt, and you've like gotten an answer together, you get credit. Even if that answer is like 100% like dead ass wrong, like you get points. So that should not be a stressful thing. The problem set's an opportunity for you to learn and see the level of things that you're going to be tested on for exams. What this also means, because you're not really getting feedback on the problem sets, is you're going to need to budget some time after the answer key has been released to go and check your challenge problems. Because when I'm grading it on effort, I'm not going to be able to like clock like, oh, this person doesn't understand anything and they need to like go back and rework that. I shouldn't say doesn't understand anything. Doesn't understand this question. Work. So, yeah, part of the thing of like not giving as much feedback is we have a really like lean staff for the summer. So like normally the pre-med class for the fall has like 20 people, and like because of that they're able to do office hours all day and night of the week, and they give very detailed feedback on the problem sets. We have me and Logan, so like we are doing the best we can, and it's also the thing of like I had the trade-off of developing kind of like higher quality instructional material or giving more feedback, and I chose to do more like developing study materials for y'all. So I'm hoping that section notes will be a really like helpful tool for studying the material. Late work, up to 24 hours late is half credit, and then after 24 hours is no credit. It's intense. It's not meant to be punitive. It's really just because as soon as one problem set is due, there's another one due a week from then. And the next problem set, this is the longest one. The next problem set is like 34 pages. And most of the other problem sets are about 30 pages unless it's only over one lecture. So like the exam weeks, it's only over one lecture. And that problem set's like 15 pages. So still a lot. But it's the thing of if you are like late submitting a problem set, then you'll get behind, then you're also behind on working on the next week's, and it can become a vicious cycle. So that's why we have such a high penalty for it. If there's an issue submitting your work, if you're trying to upload at 11:55 and it's not working, as soon as you can, send me an email with a PDF of your like problem set, and I'll try to make sure that you get credit for it. If it's like showing up and talking to me after lecture on Tuesday or Thursday, whatever, being like, oh, I couldn't get to work out, but here's my problem set, you're less likely to get full points. I would like to give you full points, so please email me and like send the PDFs. Scanning, if you are using paper problem sets, you will need to use like a camera scanner, like Cam Scanner is an easy app to use. And then we're going to be providing print problem sets to the students who requested them in a spiral bound, so you physically won't be able to like load it into a scanner. So just heads up on that. Cool. Any questions about the things that you need to turn in? I know it's riveting. It's really my favorite thing in the world. Exams. They are 65% of your grade. Woof. Woof. 2 midterms, each 15%, and the final exam is 25%. And the class is just inherently cumulative. Like, you're going to learn your first reactions in lecture 3, and then lecture 5 through the end of the course is more reactions, where, like, you have to know all the reactions at all points. Like, you won't be able to forget things. There are some, like, isolated skills from Unit 1 that won't appear in Unit 2. So, remember yesterday in class, the Newman projections, the little wheel and everything? You are 100% going to have an exam question on that on the first exam, and then you are 100% not going to have a question on that on the second exam. Because we want you to learn that skill, we want to test that skill, but then afterwards it's a tool in your arsenal, but it's not going to be something we're explicitly testing for exam 2. It will probably come back for the final, though, because the final is everything. The exams are graded on accuracy and correctness. I got that question in the past because, you know, problem sets are effort. Why not exams? But they won't let us. Group exams. So that's something that's kind of interesting. So on the scheduled exam days for the first 2 exams, you're going to come and we're going to start the exam at 8:45 instead of 8:30, so about 15 minutes late. You're going to take it for 90 minutes, an individual exam. It's typically 9 questions in 90 minutes. You're going to get practice exams and everything before. And then you will turn in your individual exam that you do. It's going to be closed book, all the normal things. Then you'll take a 15-minute break, and you'll be assigned into groups of 3 or 4. Then you'll come back in your groups of 3 or 4, and you will take the exact same exam again in your group of 3 or 4, and you'll have 1 hour. And so the purpose of it is, like, a lot of times students will do an exam and then never think about it again because, like, especially if you've done badly on it, it's like, I don't want to look at that. Yeah, it's a bummer. But the nice thing about the group exam is you get pretty immediate feedback. Like, in the group exam, when you're talking with 3 other people, you figure out what you missed. And then you also learn why, which is helpful. The other kind of way that the group exams run is you're going to work together. You can't do a divide and conquer of, like, tear apart the exam, different people do things. That isn't the point of this. But we are going to have the core staff, probably plus some lab TFs maybe, circulating in the room. And what the staff is going to do is we are going to settle debates. So let's say we have 2 people in a group and they're arguing about hybridization. And one person's like, I think it's SP2. And the other one's like, I think it's SP3. Then they can raise their hand. A staff member will come over and they can, like, present both sides. And then the staff member will go ahead and say, it is SP3. So we can settle debates. But if you're like, I don't know what to do, we can't just, like, start it for you. You can be, like, presenting 2 sides. Or if both sides presented, like SP3 and SP2, I could be like, you both are wrong. Like, regroup. Yeah.
Is the whole group submitting one exam, or is everybody submitting their own?
Whole group, one exam. So you'll typically have, like, one person be the scribe of the group, or you'll kind of, like, pass it off of different people do different questions.
And
But
how are the groups, like, is it just
randomly assigned. Yeah, because normally when we let people pick, then all the strong students congregate together, and it's not spread out. And so we want to try to make it as even or fair as we can. It's also the thing of if you're coming in being like, I'm going to get a 97 on the test, why should I do a group exam? People are the worst. Because, of course, that's how you are going to be. It can never hurt your score. So your group exam score will never hurt you. In the past, like, I think 6 years of me teaching, there have been maybe 3 or 4 instances ever where a student's individual score was higher than the group exam. So for most people, it helps out their score. And your actual score on the exam is going to be 80% your individual score, 20% your group exam score. So it can sometimes even be like up to a 10% boost, depending on how that individual exam went. But cool. Practice exams are going to be released about 5 days before the exam. You'll get 2 for each of the exams. And we're going to send out some pretty detailed instructions of how to approach it, because it's going to be a little bit of a balancing act of there's going to be a problem set that needs to be due. You're going to have the practice exams you need to be studying for a test. And then also we're going to do lecture 5, which isn't on the exam. And so we're going to be like, do this in this order. Otherwise you might crash and burn. But the last thing is, like, sometimes it just takes some processing time to, like, solidify content. And let's say you do the first exam and it's not your best showing of it, and you never figure out Newman projections or something. But then as the course progresses, you do some more practice and you're like, oh, I get it, but it's like 1 week too late. If you do better on the final exam, or if you do better on any of the exams, really, whatever your best exam is, it's going to get an extra 10% weight. So a poor performance on the first exam is not going to be catastrophic for your overall grade. So that kind of builds in a little buffer. Questions about exam?
Is there a lab during exam weeks?
I think so. I think the first one, yes. And then by the time we get the second exam, lab will be over. Because I think lab's only the first 5 weeks. But also, to be so honest, my lab philosophy is, like, not my circus, not my monkey. Of, like, I can answer any question about lecture and, like, section, and I don't know what they do in lab. I don't know the software. I don't know the assignments. I don't know when they're due. And I don't want to know. So, yeah. Cool. Any other questions on exam things? Participation's going to be 10% of your grade. It's going to be split 5% in-class poll questions and 5% lecture review quizzes. We already talked about the review quizzes to be turning in that everyone should be getting like 100 on. For participation for yesterday, because it was a little wonky, I think it was mostly the setup that was wonky, because I was touching base with Logan, and like everyone but 3 people we got the answers for. So it kind of worked out, even though it was a bit of a mess, so sorry about that. But I think we're just going to blanket. Everyone gets full participation points for the yesterday because it was like technical things. And then after that, what we're going to have is your score for participation for that day is how many of the questions that you responded to. So you don't have to get the questions in class right, you just have to submit answers. So what that means though is like if you like go to the restroom and a poll question happens while you're gone, like we can't really do anything. Like your score for participation that day is going to be what it is of like how many were answered. But we are going to drop your 2 lowest participation scores. Because of that, we're not doing like excused absences. Like if there's a day that you have to be gone, or like if you're sick or something, like we just don't have that built in. But also it's 5% of the grade. The stakes are pretty low for it. And think about like missing one question. That's like maybe 0.2% of your final exam, maybe, and that can be dropped. So if there are issues, we will address it, but that's kind of the policy right now. Cool. Section. So many of you know what section is because you've taken classes at Harvard before, but it's a chance for reviewing material and practicing. No new material is going to be introduced in section. I might just reframe things or kind of present things in a more condensed fashion. And general section structure, I'll talk about it when I switch over to the iPad in a bit, but we'll do kind of an overview outline of what happened in lecture, just because I kind of assume that like after a 3-hour OCHN lecture, y'all are like destroyed, like in terms of like, what was that? What's going on? And now I need to like pick up the pieces of, okay, there were 4 big things that we did. We're going to talk about these 3 and do this practice. And so it's going to be a mix of like content review and practice together, mostly because when I was an undergrad, I didn't go to section. And part of it was because in section, sometimes they just like start working on problems. And I was like, I don't remember this or know how to do this. And you're just like telling me to work on it. I can do that on my own. And then, yeah, we'll talk more about section structure once we get into the actual section document. On Fridays in section, we're going to be doing extra challenge problems, which are already posted, and if you are getting printed problem sets, it'll be in the printed like handout. Extra challenge problems are not extra challenging, they are just additional challenge problems. So they're exam level problems. The only thing I ask is don't look at the problems before coming to section, because we want to kind of approach them fresh as if it were like a new question that you were seeing. And then like after that section is passed, by all means, work through the problems, take your time. Then section is not mandatory, but I am taking attendance. I already gave you my little Orgo duckling metaphor of like, I just want to make sure none of the ducklings were eaten or harm has befallen them. My communication preference is email. Email is my to-do list. Sometimes I can be real fierce with the email. Like sometimes I'll get an email and respond within 3 minutes. Like I'll be walking down the street, see an email, blah, 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 gone. But it's not on my radar or to-do list unless I have an email about it. So you're welcome to come talk to me about things. But oftentimes, if it's something I need to do for you, I'm going to be like, can you send me an email with that? Yeah. Also, it's colton.harvard.cam@gmail.com because they shut down the g.harvard accounts, like when I'm not here in the summer, like it's off and on. And so I just wanted like a Gmail where it's always active. Yeah, try to give me like 24 hours to respond or like over the weekend if it's a weekend. But also, I remember Harvard, send a bump email. Like, just annoy me until I answer you. Last thing, section notes. I'll post the blank section notes PDF before class and an annotated one probably at the end of the day for section days. We're not providing printed copy of the section notes because they use a lot of color. So like I printed out one for me for just like a reference, and truly to print this out was like 40 pages just because like color is so heavily used, and I think black and white, like it would be like kind of what's the point of like doing all this without color. So we don't have a printed version. If you want to use it on the iPad, you are welcome to, But the other thing about the section notes is they are pretty condensed. So the way I've formatted and why I've done it this way is because I'm using the iPad and I can like zoom in on the columns. The second reason I've done this is because lecture notes are so spread out over like 30 pages, and I want you to have a condensed resource that covers all the highlights from the lecture. So having a 6-page thing to refer back to instead of having to search through 30 pages, I think is easier. And sometimes section notes are only going to be like three pages, but cool. Question?
Yeah, if you were talking about the iPad, I'm very curious about why can't we use technology in lecture there?
So I'm gonna be so honest because I use iPad for everything, and you can use iPad in section. I don't care. But like truly in May, I did a Maymester class, and I was using my tablet to take notes. And then when I got bored, I would go and switch over to do something else. I wasn't engaged. Part of it was like the class was really easy, and like it was taking differential equations, and I like am almost done with the math degree, and so I was like, this is fine. But it's like it's easier to stay on topic if you don't have the choice other than to focus or be bored. Like when you have your phone or tablet, it's just more distraction. So again, as a longtime tablet user, I understand the frustration, and I also am like, yeah, no, I would focus more if I didn't have access to it during class. But I know. Okay, so transitioning from the course logistics to resources. So TFs, but really like TF singular. I'm here. Please reach out for help. I also like stick around for questions after lecture and after section. Then help room. We talked a little bit about this yesterday, but help room is going to be in this room on Mondays from 10:30 to 11:30, 12 to 1. And normally that'll be stopped by Logan, and then in the afternoon, me from 3:15 to 6:15. It is going to be swapped for this coming Monday, where I'm going to do the early ones, Logan's doing the late ones because he has a conflict. But you can come to any or all of it, and it's a space for y'all to work on the homework and have core stuff around to answer questions. It's not traditional office hours, and I'll get to that a little bit more in another slide. So things to potentially get, can I get a show of hands who has gotten model kits? Okay, ding dong. So lecture 4, which is going to be next Thursday, it's about the 3D structure of molecules. And it's something that me personally, when I was learning OCHEM for the first time, I would not have been able to do without a way to visualize it. And I did all the Calc 3 things. I'm like, oh, I have good spatial reasoning. There's something about being able to build it and see it that just makes it infinitely easier. So I'd recommend trying to get a model kit before then. The one at the Coop is $200 or something crazy. Don't do that. Get a $15 or $20 one from Amazon, or, the Cabot Library in this building. If you go down to the basement, you can check out a model kit to use. And I think that you can check it out for the whole summer. So, also do that. If you don't even want to go to the library, third option, find a friend who has a model kit.
20-30 friend is best. Because, if they're taking 20-30 and you're taking 17-27, your classes will never overlap.
Yes. So the other version of the summer organic chemistry is Chem S20, where they are doing OCHEM 1 and 2 and getting credits for a whole year's worth in 7 weeks, which is crazy. They have a test every week and 2 or 3 hours of lecture every day. But yes, so source a model kit however you will. The last thing is, do y'all know the, I think it's the Academic Resource Center during the semester for Harvard College students that does free tutoring or something like that? There's a summer version of that where you can get free tutoring, and that's for anyone, not just Harvard College students. It's called the Academic Tutoring Services. And I have a link here. And also these slides are on Canvas. These are under Detailed Course Logistics under the General Information tab, so you'll be able to see it later. I think it launches on Sunday, so next week if you want to go, you can request free tutoring for this class. Oh, and then the other things to potentially get, we don't really have a textbook, but I love the OCHEM as Second Language books. Truly, that is how I learned organic chemistry, because I had a not very good professor and a really dense textbook. OCHEM as a Second Language just boils down the concepts into very simple English, and then does very targeted, quick practice of you need to know this skill, then you need to know this skill, then this one, then you need to put them together. And it'll do drills of do this skill 10 times and practice it. So it's really, really helpful for getting down a lot of the basics. The one weird thing, and you should know this about your experience in S17, Harvard teaches chemistry differently than 90% of the other universities in the United States. So normally, a university would have a 2-semester OChem sequence where in the fall you would do a bunch of naming, spectroscopy, like the shape of molecules, you do some reactions, and then OChem 2 is way more reactions. What we do here at Harvard is Chem 17 takes all of the organic chemistry from 2 semesters of organic chemistry, like the normal, like another school, takes everything that's relevant for biochemistry. So 17 has a mix of OChem 1 and OChem 2 content from other classes. So if you are in the Brown Coalition and you're going to take OChem 2, your OChem 2 class at Brown will likely include some stuff that we are teaching you now, and then y'all's OChem 1 likely is going to have some stuff that we aren't covering. So just be aware of the gaps and things. But also what that means for the OChem as a second language books is instead of just one book, there are 2 books split up as first semester topics and second semester topics. Because we pick and choose from all of them, I've made a concordance table here. So like for lecture 3, it's in the second semester book and it's these chapters. But in lecture 4, it's from the first semester book and it's these chapters. And it really is kind of like mixed throughout. Like Harvard does their own thing. But I actually quite like the way that we do it. So your question might be like, okay, if 17 is all of organic chemistry in one semester, then what is 27? What is the sequel to this class? Well, it's essentially biochemistry. Like you are learning the organic chemistry of glycolysis and the Krebs cycle. But it's all in biological settings. It's none of it's like lab, bench work kind of things. So, any questions about the resources? Work? Help room, we talked about this a little bit yesterday. Y'all outnumber us. So if we have a like single file line for questions in help room, it's going to lead to people getting very frustrated. And so that system just can't be the system that works for us. So you are going to be expected to work with other people in the group. So like, let's say you come to help room and you're like, I can't figure out challenge problem 3 and 5. Find other people who are working on those challenge problems. You can literally say it's not loud. Like, is anyone working on challenge problem 3? Get in a little group, try working on it. And then if y'all get stuck, you can raise your hand and then the core staff member will go and help you. And then let's say I help out one group with challenge problem 3. And then I go along and then someone else comes and says, can you help me with challenge problem 3? I'm going to be like, do you see those lovely people over there? They just finished challenge problem 3. They can explain it to you. And it's going to be kind of that situation where it's going to be facilitating y'all learning together, which I know is not ideal, especially when you're used to the Harvard pre-med classes where you have a core staff of 20 and you have all the office hours and everything. So it's a different system. The thing I will say is like the people who do show up and like work collaboratively, it can be quite an enriching learning experience. Like when you have the opportunity to teach someone else how to do something, you learn a lot through that. So I would say don't knock it till you try it. But then you still might have some individual questions. So places to go for that are lecture breaks or after lecture section. We stick around. You can email me. And then if it's like a deep conceptual question, I might just be like, let's just like talk about it at some point. But yes, and then if there aren't many students in help room or if it's like chill, then you can ask individual questions, but we're going to prioritize group questions. So can I get like a thumb meter? Do you understand help room expectations, or are you like, I'm confused with this? Okay, we're going to reset. I'm going to do another thumb meter. How do you feel about this help room policy? Are you like, this sounds like it'll be great, or like, I'm going to hate this? Okay. You know, that's more than I can expect. I probably would have done this if I was in your position. So I appreciate y'all being open-minded for it. Grade cutoffs. So in the past, we've been a bit ambiguous about the plus-minus cutoffs. We've decided not to. So here are the grade cutoffs. A minus is 92.5. A minus is the 85 in the syllabus. And then for the ones that have like 3 in the range, it's every 5%. So this is what we're going with. We are never going to set the cutoff higher than this. We could be more generous and like lower it a little bit, But we are not going to know that until we have all the grades at the end of the term. Because, like, if on the whole everything was worse and, like, only 3 people would be getting A's, we're going to lower it so more people get A's, you know? But we're not going to know how much we're going to lower it or whatever until we have all the grades. So don't ask. Yeah. My teaching philosophy, I'm here to help you. Like, that's literally my whole job. I'm here to advocate for you. If there's a chance for you to earn points for something, I want you to earn those points. Like, I'm trying to argue on your behalf and work with you. So that's just kind of like where I'm coming from broadly. Sometimes when I answer questions, I can be a little sassy, but I think that's more of personality, and it's not meant to be like a shady kind of thing. Advice is like 35% of the class of the homework participation lab, maximize those points, just because you want as much buffer as you can for your exam scores. Take skill builders seriously, so some sort of balance between just copying the answer and then just looking at the answers and taking forever. If you show up to no other section after this, the most important section will be next Wednesday, section 3. So in lecture 3, you will learn your first set of reactions, and reactions are kind of fundamentally a different type of information to learn than your other science classes. Like a bio class, you have like vocab, you have terms to memorize. Chemistry, general chemistry class, you're kind of learning math and like little algorithm formulas. But reactions, they require you to like study them in a different way. So I'm going to do this how to study reactions tutorial for like half of it. And then last thing I would suggest is like make a schedule for your work for the class just to help keep you structured. It's probably going to be like 10 or 15 hours a week outside of class just with how busy everything is. So like here I just kind of put together an example like schedule of like we have class section, we have lab, and then the orange is the stuff that you can control. And I might just be like, yeah, I'm going to go to the library and work on this between 6 and 8 every day or whatever your schedule is. I also put sleep on the calendar because for me personally, if I don't put it on there, it doesn't happen. But all this to say, and you'll have this as a resource, reach out for help when you need it because it's an intense class and we're here to help. So let's take a little break for like 90 seconds to really like stretch your legs, check your phone, like, and then I'm going to transition over to the iPad and then we'll pick up from there. And then for the people that came in late, the QR code is up here for the attendance thing. I do not, sorry. And like the system's a little bit like crazy. Yeah, sorry. Does anyone by any chance have an extra, you said iPad charger? Okay, so let's transition to like normal section format things. So first off, I'm just going to give you an overview of like the first page of section notes. Or actually, I'll go through the outline. We're going to talk about this like first page things. We already did the PowerPoint here. And then there are 2 main topics that we are going to cover today. We're going to cover some basic skills with like hybridization bonding, and then we're going to cover resonance. There are also 2 other big topics that were new, nomenclature and conformational analysis. For those, what I've done is I've made videos for them as just a little QR code that you can scan. It's a YouTube video that just does a brief rundown of it and then works some problems related to it, which the problem page did not copy for some reason. But Same thing for Newman Productions, where I have like a rundown of it and then a video. You might be like, well, okay, why are we not covering the new stuff in section? And it's kind of because the new stuff is a little bit more isolated. Like, yes, you are going to have a like 5 points on a test be a nomenclature question, but one, it's pretty easy, and then two, it's like its own isolated skill. Conformational analysis, it's a little bit more involved, but it's its own isolated skill. Whereas if you guys don't have this down, especially for like tomorrow and like next week, then it can be like catastrophic. Because resonance is one of the most important topics in the class, and so I want to make sure that y'all are really solid on that and have a good idea of bonding. The other thing is for the hybridization and bonding, tomorrow in lecture is molecular orbital theory, which is kind of a souped up version of like bonding and molecular structure. So I want to make sure that y'all have a good foundation for that. So that's kind of why that decision was made. But, so first page of section notes will always have the QR code for attendance, and yes, they will always be specialized for whatever lecture and have a little image. Then I present kind of like an outline of all the lecture material that you covered on the previous lecture. And I try to do a highlighting system to show you how important things are. So it's hard to tell on this screen with the projection, but these are orange and these are yellow. Orange is a heavily tested material. Yellow is important content to like master, but it's not super, super heavily. And you can see the alkane nomenclature and conformation analysis are these yellow level things where they are tested, but they're not the hugest topics. And then not explicitly tested are the gray highlight here. So we're never actually going to ask you what's the electron versus molecular geometry or anything like that, but it is a good thing to know, like it's a helpful skill. And then the things that are not highlighted are somewhere in the middle in terms of importance, or they kind of like fold into other things. So I'll do that for each of the lectures. Then you might have heard from some people in the past that organic chemistry is all memorization. Those people are lying to you. You might have also heard that organic chemistry has no memorization. They are also lying to you. There will be some things that you have to memorize and some things that are like skills to learn, and I like to just try to be as upfront with the things that we do want you to specifically memorize. So like the organic chemist periodic table thing that Logan mentioned yesterday, the electronegativity trend of increasing up and to the right, the master table of bonding hybridization of like 3 electron domains is sp2. We want you to have that down cold, like just memorized. So whatever system you use for memorizing things, flashcards, whatever, do that. Things to specifically not memorize, don't memorize the like energetic cost of like the Gaussian eclipse interactions. We'll always give you that. Like go crazy on it, but don't go that crazy. Don't waste your time. And then I've also just listed out some skills to be practicing and developing as you're working through the problem set. And so you can treat this as like, check mark, I know how to do these. Then I have a little meme section at the bottom. Like for today, we have your extended NFPA hazard diamond that includes the street value of the substance, the number of federal agencies who want to know if you have any of it, and the number of times it's caused terrifying lab accidents that keep chemists up at night, basically. Yeah, these are kind of generic. These are XK, CDE cartoons, but once we get into more niche topics, we will get more niche memes. The QR code in the bottom of the first page is always going to be a section feedback form. And it's going to be the same QR code for all of them. So after section, if you're like, this went well, this didn't, and want to give some feedback, I like make changes every year. I like record my sessions to like take notes on it and see what worked and what didn't work. So, cool. So the big things that we're going to do today are the basic skills and the resonance and arrow pushing. We'll do a little review and then some questions. Any questions from y'all before we jump into that? Ding dong. Okay, so first off in basic skills, formal charge. In Gen Chem, you have the formal charge formula here with number of valence electrons minus lone pair electrons minus number of bonds, and it was like math. It was like an equation thing that you did. For organic chemistry, you want to switch this to being a visual skill, where you see how many bonds something has and you know what the charge is. So like when I see a carbon with 4 bonds, I know it's neutral. When I see a carbon with 3 bonds and no lone pair, I know it's positive. When I see an oxygen with 3 bonds, I know it's positive. 2 bonds neutral, 1 bond negative. And similarly for nitrogen and the halogens here. So you want to be able to kind of visually spot the formal charge rather than having to do, okay, oxygen is 6, and minus the 3. Like, it just takes too long. So can we try doing a practice of the visual identification of formal charge here? So what is the formal charge of this carbon? 0. What's the formal charge of this carbon? -1, because 3 bonds in a lone pair is negative. This one? 0, 4 bonds. What about this oxygen? 0, 2 bonds, 2 lone pairs is its happy state. What if it has 1 too many bonds and is this one in the middle? Plus, like H3O plus, and then this one? Minus. Great. As quick as that is, that's how you want to be. Then, moving on to skeletal structures. So it's our abbreviated graphic notation. Use skeletal structures. I know it might feel a little bit like harder at first, just because like it's a new system. But if you're drawing out the CH3, CH2, whatever, you're going to hate life. Like the OChem class, when I learned it for the first time, they used the CH2, CH3, the whole condensed structure the whole time. They never used skeletal structures. I was like, God, like why? For what? But in skeletal structures notation, every end or bend is a carbon. So this is a carbon, this is a carbon, this is a carbon. All CH bonds are implied. Lone pairs we can generally have implied. You can draw them out if you want. But formal charge is not implied. So formal charge has to be explicitly given. Then for atoms that are not carbon, we do have to write out the hydrogens. And we call atoms that are not carbon heteroatoms. So let's look at this one up here, this carbon. How many hydrogens are on that carbon? 3. And we know it's 3 because it's neutral. So carbon neutral has 4 bonds. And we see 1 written down. So we know that it has to have 3 hydrogens that are hidden on here that we're just not seeing. What about this carbon? 2. It has 2 bonds written, so it must have 2 hydrogens. What about this carbon? 0. It already has all the bonds, so no hydrogens. And then what about this one? 0 as well. Because if it has a positive formal charge on the carbon, we know it's 3 bonds, no lone pair. Great. And then over here we see that when we have a positive charge on an oxygen and it has a hydrogen, we have to write out the hydrogen. We can't imply it. So it would be wrong if you just did this. Also, skeletal structures just let us quickly draw the actual structures. So heptane, hept is a prefix for how many carbons? 7. So we do 1, 2, 3, 4, 5, 6, 7. Done. Easy. Over here, we have a parent name at the end, pentane. So there are 5 carbons. 1, 2, 3, 4, 5. And what is hydroxy a prefix for? Yeah, like an OH to add. So our locator here says that we put it at position 2. So we count 1, 2 from the end or 1, 2 from the end. Does it matter which side that we count? No, if we're drawing it, we are playing God in that situation. So we just decide what side is 1 and then we put it on there. So I'm going to just put it here. Done. And again, more nomenclature things later, but in terms of the skeletal structure notation, that's the biggest thing. Yeah.
I have a question. How picky are you guys with like answering questions? Like, say we were given something in like skeletal structure, it's like new resonance, and you want to kind of like draw it out like all the lone pairs and stuff.
So we're never going to grade you on lone pairs unless the lone pairs are involved in what you're doing. So like, let's say you're doing a reaction where the lone pair goes and attacks something. We want you to draw the lone pair there. If the lone pair is just sitting in the corner, you don't have to draw it. You can imply it. Yeah. Good question. Okay. Hybridization. So this might be where I like start to lose y'all's generation. Did anyone here know the DS game Cooking Mama? Yes? Okay, we have some Cooking Mama fans. So I imagine hybridization kind of like Cooking Mama. Of you lay out all the ingredients and then you put it in the pot, you stir it together, and it comes out like the finished product. So takes the raw ingredients, finished product. And you are only going to hybridize the number of orbitals that you put in. So like, let's say you put in 3 orbitals into the little Cooking Mama pot to hybridize, you get out 3 hybrid orbitals. And the p orbital that's left sitting on the kitchen counter is going to stay there and still remain a p orbital. The other kind of big idea here when you hybridize is no matter what, if you start off with 4 atomic orbitals, then after hybridization, you still have 4 orbitals. It's just the identity of those have changed from being these pure SNP orbitals to being hybrid sp2 orbitals and a p orbital. So again, I know that you all have seen that before, but I just wanted to bring it up. Then we have the geometric layout that's associated with each of these hybridizations. So sp3 hybridization is the hybridization that in 3D is going to space out 4 things as far as possible. So it's our tetrahedral geometry here, where it's like 4 corners of a little pyramid, and it's just trying to get everything as far away as possible. If we only have 3 electron domains, then we are going to be in the sp2 case, where we want to spread 3 things out as much as possible, and that's going to be our trigonal planar. And then finally for sp, we have our linear, spreading out 2 things as far as possible. We already talked about sigma bonds and pi bonds yesterday. Pi bonds are only between p orbitals, so that's the big one to remember. And then multiple bonds, you always are going to have a sigma bond as your base, and then any additional bonds that are present are pi bonds. So double bond is going to be sigma and pi, triple is sigma pi pi. So with that, let's look at this first practice, which is on page 6 of the problem set, Skill Builders. So I want to go through with y'all drawing this out very explicitly, and then also talking about which orbitals are in which bonds, because that's going to be a skill that's going to help you tomorrow when we get into molecular orbitals from atomic orbitals. So first off, what's the hybridization of this carbon? SP. How did you figure that out? Well, what is the thing that you first asked yourself? Yeah. Yeah, the first thing we asked is how many electron domains. And there's 1 electron domain here, 1 electron domain here, 2 total. And then per our like table of master whatevers, 2 electron domains were sp hybridized. Great. Another thing. This is side note. I am horrible with names. Like truly like maybe clinical. Like I've been walking on Oxford Street when I was an undergrad. Someone came up to me and said, "Hi Colton, ask me specific details about my life." Like a deep cut. I had no idea. Like not even the name. I didn't even remember who it was. I will learn everyone's name by the end of the course. But to help me along with that, when I call on you or when you ask questions, can we use the format of, "Hi, I'm blank. My question is blank." Just so I'm hearing it, and then I'll probably like repeat back your name. And then you can stop doing that when I independently start prompting you on your name. So like if I like say, "Hey person, what's your name?" Like, no. What, give me your name. Yes. Say one more. Marcos. So if like in the future, I'm like, "Hey Marcos, what's your question?" Then you can stop introducing yourself each time. But until I get to that point, I will need the support. So thank you. So we're exactly right. And then this nitrogen over here, it's a little sneaky. Does this nitrogen have any lone pairs on it? Yeah. How do we know it has lone pairs? It has no formal charge. Remember, our skeletal structure rules are we have to explicitly state any formal charges. This one has none, so we expect it to be neutral. But we only see 2, 4, 6 electrons connected to that nitrogen, so we know that there are 2 more. Okay, so now electron domains, how many do we have on this nitrogen? 2, so it's also sp hybridized. Cool. So I have written out all of the orbitals then that these atoms bring to the table as they go to make the molecule. They're doing like construction, I'm so sorry. So the carbon, we're going to have 2 sps, 2 ps. The nitrogen, we're going to have 2 sps, 2 ps. Hydrogen so teeny, only has an s. Cool. So let's try to map all of this out. So we have an H, we have a C, and we have an N. Now, let's say I wanted to figure out which elements are in this sigma bond. So we have a sigma bond here, and then here we have a sigma and 2 pi's. So we know that the only orbital that hydrogen can contribute here is this HS orbital. But then, hypothetically, this carbon could use an sp orbital or a p orbital to do a sigma bond here. It's uncommon, but you can do p orbitals in sigma bonds. So how do we figure out which one was actually used in this situation? Does anyone have any ideas?
Well, you kind of have to use p orbitals for the triple bond, right?
That's exactly it. So, if we have pi bonds, we know pi bonds have to use p orbitals. So let me go ahead and like map out how these orbitals are going to be used in those pi bonds. So we are going to have one pi bond using this set of p orbitals. And then we are going to have another pi bond using this set of p orbitals. And that's the only way that we can do it because pi bonds are only between p orbitals. So if our pi bond or our p orbitals are used up in the pi bonds, then the only other option of an orbital that carbon can contribute to this bond is an sp orbital. So we know that that sigma bond is going to be between the hydrogen s orbital and the carbon sp orbital. So this is sigma CH. So let's draw what that looks like on the molecule here. So the hydrogen here, the s orbital is just a little sphere. And then for carbon, our sp orbital, it's going to be kind of an unequal p orbital, like an unequal dumbbell, where we're going to have a big lobe like this, and a little nub on the other side. So, bloop. Bup, 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 bup. So that is our hydrogen s orbital, carbon sp orbital, making a sigma bond. Okay, let's go ahead and do the pi bonds while we have them in here. So one set of the pi bonds are going to be above and below. And we can connect them with little lines here just to show that's going across. And then our other pi bond also has to be perpendicular to the other axes. So if our sigma bond is in this kind of like x-axis of the plane, and then here our first pi bond is like in the up and down axis, then we need the third one to be in the kind of into the page, out of the page axis. So we are going to do bum, 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 bum. So those are our pi bonds. And then what we have left is we have the sigma bond between carbon and nitrogen here. What's our only option for what orbitals each one of them contribute? sp for both of them. So let's draw that out. So the carbon's sp orbital is going to be there, and a little nub. Bup, bup, bup. Nitrogen's going to be there, and a little nub. Okay, we have one leftover sp orbital. What's going on with that? The lone pair, exactly right. So we are going to have this nitrogen be our lone pair, nitrogen sp orbital. So we draw the sp orbital over here, and we can just put our little lone pair electrons in it. So that is the level of understanding we want you to have in terms of like, what are the bonds, what orbitals are made up of, and how do they all fit together. Now, on an exam, we are probably not going to ask this specific thing, but this is the type of thing that you will need for molecular orbital theory tomorrow, which is why I wanted to cover it. Any questions about this process or anything with like hybridization or any of these basic skills? Yeah.
How did
Marcus.
you know that? Oh yeah, sorry.
Yeah.
That one of the like sides of the carbon is larger than the other.
So, for the sp, like the hybridized orbitals, there's always a bigger lobe and a smaller lobe. And the bigger lobe goes wherever bonding is happening. So if we are making a sigma bond here, we're going to put the bigger lobe of the sp orbital there, and then the small lobe over here. Good question. Yeah. Cool. So now we're going to pivot into resonance, which I know that you'll have heard before, but the way that we conceptualize resonance in organic chemistry is a bit different than most general chemistry classes. So a classic example of resonance is benzene here. So C6H6, where the structure, if you draw the Lewis structure, it looks like alternating double and single bonds. But we know at bond length that double bonds are shorter than single bonds, so we would expect it to be this like cattywampus thing, where we have long bonds and short bonds. But then when we do a crystal structure, we see actually all the bonds are the same. And the length is somewhere between the double bond and single bond length. So basically, resonance points out a failure of our notation system for molecules. Lewis structures can do a lot, but when we have resonance, there is bonding that is happening that we cannot accurately represent with one picture. That's why we do two resonance structures, and we use this double-headed arrow to show that two things are in resonance. I really like this metaphor of like, neither of these things exist, and the real thing is kind of a mashup between the two. I think that that's a really good way to think about it, your resonance hybrid. That being said, even though this is like really what the bonding look like, it's kind of between double and single bond for everything, we don't use this for organic chemistry because it's a harder notation. Like, again, we've built up such a robust notation system for chemistry with the Lewis structures. We want to use them as much as we can. So that's why you will never really be drawing this, but you should understand that that's what the actual bonding is. So, big key idea. Resonance, we said, is a failure of like our Lewis structure system, but what causes resonance? Like, why does it happen? And resonance happens when electrons delocalize. So think about like local area, small, contained, delocalize, spread out. So delocalization is when electrons are spread out among 3 or more atoms. And the requirement for delocalization is you have to have p orbitals to delocalize. So let's think a little bit about like, why do we need p orbitals to delocalize? Well, if we don't have p orbitals and we have kind of sigma bonds, the electrons are between the nuclei, and then they will hit the nuclei. They can't go through the nucleus or anything, and so they have to be localized to just their little pockets here. Whereas when we have p orbitals, we put the electron density above and below the nuclei, and then it can spread out for as long as we have p orbitals. If I had another p orbital here, it could delocalize even further. And so that is why like p orbitals is the big thing that allows us to delocalize electrons. Now, why do we care? Like, why do molecules delocalize? Mostly because it's stabilizing. Like, there is just an energetic savings that you get by spreading out your electrons over a molecule. Think about trying to keep electrons negatively charged in a small space. They're going to want to both repel from each other and also, like, repel against, like, other negative parts of the molecule, like, especially if you have a buildup of a negative charge. And so anything that you can do to spread out that charge, it makes it more stable for the whole molecule. The second big idea here is the more stable a resonance structure is that you draw, like a Lewis structure, the more stable it is, the more heavily it actually represents how the bonding is taking place. So let me show you an example real quick. So I can technically draw a resonance structure that takes the electrons in this pi bond and moves them to a lone pair over here. And now this carbon has a lone pair and this carbon has a carbocation because we just robbed it of electrons. Do you think of these two resonance structures, which one is better, the top one or the bottom one? The top one's more stable because we don't have any charges. So which do you think gives us the better idea of the actual bonding of the molecule? Well, the top one does. So it's going to be a more neutral bonding than this kind of dipole situation here with two charges. So this is much more heavily contributes to the actual bonding. So just some criteria here. Stable resonance structures are ones that have complete octets. They have as few formal charges as possible, and that's what we just saw in the example that we just looked at. And then it puts negative charges on things that are more electronegative and positive charges on things that are less electronegative. So like, let's say your molecule has to have a negative charge, and you have the choice to put a negative charge on an oxygen, nitrogen, or a carbon. Who likes the negative charge more? Oxygen. She's electronegative. She has a high electronegativity. She loves to hug onto the electrons. So oxygen's just going to be chilling with a negative charge. Whereas if you try to put a negative charge on carbon, she's about to crash out. She's going to be a little angry. So that's kind of what we keep in mind when we're ranking stability. Similar thing for a positive charge. If we're putting a positive on oxygen, she is stressed. She does not like it here, and things are going to need to resolve itself quickly. Whereas a positive charge on carbon is like, like it's positive charge, but it's not nearly as like urgent. We have some rules for drawing resonance structures. So you should never be like deleting electrons or adding electrons. Your number of valence electrons stays the same. You're always going to have the same connectivity in skeletal structure. So we're about to look at this practice here where we're going to draw some resonance structures. And before even beginning, before even like doing any thought, one thing I could do is I can go ahead and write out the single bond framework here because I know that that's not going to change. All of that has to stay the same. All the connectivity, all the atoms has to stay the same for resonance structures. The only things that are going to be moving around in the resonance structures are going to be the p orbitals and the pi bonds and lone pairs and things. The hybridization of all atoms have to stay the same, and then I already said this note of the more stable structures have fewer charges. Now, have people used curved arrows before in their Gen Chem class to show like movement of electrons? Can I get a show of hands? Okay. For the people who haven't, I'm going to start from scratch. Curved arrows are going to be one of the main things that you do in this class, and it is a tool for us to show the movement of electrons. We primarily are going to use what's called a double fishhook arrow, which just looks like a normal arrow that's curved. And this denotes the movement of 2 electrons. These are going to be the arrows we do for a majority of the class. But then once we get to lecture 9, we're going to talk about radical chemistry. And if we only want to show 1 electron moving, we use a single fishhook arrow, so just on one side. So we're talking about the movement of electrons. We also have just a bunch of arrows, so I just tried to include like a key of, you might see some other arrows. These are what they mean. But let's think about this scenario where we're trying to show the movement of 2 electrons. What are potential sources of electrons? Lone pairs. Great. Also, if you had a charge on a molecule, what do you think would be a good electron source? A positive or negative charge? Negative, because we have a buildup of electrons. So negative charges, lone pairs. Another good source is like a pi bond, so you'll see that sometimes. And then we have to move those electrons somewhere. So the other thing with curved arrows that if you're new to them is important is arrows have consequences. If you move the electrons from one place to another, then in your next structure you have to show the consequences of those arrows. So let's see it in action here. What's a good source of electrons in this molecule? The oxygen negative charge, right? And so we know that this has 3 lone pairs. We don't necessarily have to draw all of them, but I'm going to do it just for practice. And then how many lone pairs does this top oxygen have? 2, because it has 2 bonds and it's neutral. So if we are looking for a source of electrons, we're going to start our arrow from a lone pair of the oxygen down here. And let's make it into a bond with this nitrogen. So what that means is in the resonance structure that we're drawing, we now will have created a double bond by putting these lone pairs into a bond, a pi bond with the nitrogen. And that means that this bottom oxygen only has 2 lone pairs left. Now, this is why I had the sound cue. Nitrogen already has 4 bonds, and if you tried to just do this, we would call it a Texas nitrogen because everything's bigger in Texas, and it's also Texas nitrogen because it's outlawed. And then I would normally play. It didn't play. Woo! So that's what that sound cue is for. But then we have the Texas Coalition. So given that, we have to break a bond on the nitrogen because it already has a full number of bonds. And the only types of bonds that we can break in resonance are pi bonds. So we are going to break this pi bond and move the electrons onto the oxygen. So now that oxygen is going to have 3 lone pairs. And the last thing to check here is what's the formal charge? So oxygen with 1 bond, 3 lone pairs, what's its charge? Negative. And then a nitrogen with 4 bonds? Positive. There we go. So that's kind of how we put the things together. And because the arrow pushing is pretty new for most of y'all, I want to kind of more explicitly state some rules for valid moves for resonance arrow pushing. So there are really 3, and I think only 3 things that you can do for resonance arrow pushing. You can do a bond to a lone pair, which we saw in that first example. We can do the opposite of that, of a lone pair into a pi bond, which is what we just did on over here, a lone pair into a pi bond into a lone pair. And then the third that we can do, and it's typically only with cations present, is we can do a pi bond to another pi bond. And so we move our double bond over here, and now this one on the left side is robbed of electrons. So with that, take a couple of minutes and try out this practice where you are going to be drawing the resonance structures. And then if you finish those, think about which resonance structure between the 2 is more stable. So I'll give you like a minute or 2. So I know we probably don't have it all done, but for this second example, what's a good source of electrons? Yeah, the negative on the O. And so for that, we know that the actual things that we are going to be moving are the lone pair electrons. So that's where we would want to draw the lone pair here, because we're going to move it. And then the only thing that we can do if we have a lone pair is we can do a lone pair to a pi bond. But then this carbon already has 1, 2, 3, 4 bonds, so we have to break a bond, right? What bond are we going to break? The pi bond, the only thing we can. And then we're going to move it over to one side of the bond. So the top arrow creates this second double bond. And I'll put the consequences of the arrow here in this light blue, just to see like this arrow turned into that bond. And then this arrow here became a lone pair on that carbon. Yeah.
Some of the questions say like, write out 3 or 4 resonance structures. Like, in a kind of more problem set exam scenario, are you guys mostly going to be asking for major resonance? And I ask that just because some of these are like really unrealistic resonance structures. Like,
Yes.
I don't know, if you ask for 2, you can send one from like oxygen to the carbon and then push it
No,
back.
totally. Like, I mean, you could do a resonance structure where you only did this, and then what you would have is bum, 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 bum. You would have a negative here, a positive here, and a negative here.
Yeah, exactly.
So that is going to be like so many charges that it's probably not going to be a major contributor to what the real bonding is. So this is one that we wouldn't ask you to draw, but we'll be very specific in an exam setting on how many resonance structures we want. And like, again, these are kind of simple examples to get us started. They will get more complicated and you will get more practice with it. So you'll see it as we go. Yeah. Okay, and then over here, the only thing that we have on the bottom is a pi bond for a source. So a pi bond can turn into another pi bond, and we shift it over here. When we shift it over here, the positive charge gets moved to the other carbon. So now, between these two structures, which one is more stable? They're the same, because they both have positive charges on carbons, so it doesn't really make a difference. Okay. But this one, we have a negative charge on carbon versus a negative charge on oxygen. So who likes to have the negative charge more? Oxygen. So we would say the one in this box is less stable. Then finally, the top one, we have a positive on nitrogen, negative on oxygen in both of them, so it's equally stable again. Yes?
So when it asks you to draw like the best possible resonance structure, if you follow these like kind of arrow rules, will it kind of naturally pick the best possible one, or do you want us to consider other ones?
So, I mean, this is the thing, like, here, this is the best resonance structure, and so it would be weird for us to ask, give us the best resonance structure if that's what we give you, but, like, if we gave you this and say, draw the best resonance structure, we do that. Typically, we will say, draw any major resonance contributors that contribute to the actual bonding of the structure. And so that's the thing that I think when you see more practice and when you see more like answers, you'll get a better feel for. Like, it's hard to have a blanket statement for it right now. But good question. And your name?
Oh, Ronnie, sorry.
Ronnie? Burke. Yes.
My name is Matska.
Matska.
So the thing is that in Gen Chem, when we refer to resonance, we mostly were referring to the equally stable ones, but now we're just referring to anything that
Yes.
can work, even if it's like not stable or like not very possible. We're
Correct.
still referring to it.
Correct.
Okay.
Yes. Burke. There's one last topic that we have before we go. And you learned about this in lecture, but I didn't think that this had a good publicist for it, so I tried to do some branding for her. So, you know the master table of hybridization of like 4 electron domains is sp3, 3 electron domains is sp2, and then 2 electron domains is sp. There's one major exception to that, which I decided to brand as the neighbor rule. So, atoms that 1, appear to be sp3 hybridized. They have 4 electron domains. 2, they have a lone pair. And then 3, they are adjacent to a pi bond or an empty p orbital. They will in fact be sp2 and not sp3. So let's kind of look at this image and think about why. So here, this oxygen has 1, 2, 3, 4 electron domains. It appears sp3. It has a lone pair. And it's adjacent to a pi bond. Note that if the pi bond was right here, the oxygen would be part of the pi bond, so it's not adjacent to it. So the pi bonds in the neighbor. And then for this, what we are going to think about is, well, this pi bond has 2 p orbitals, right? And let's say hypothetically I was an oxygen. And I could put my lone pairs in an sp3 orbital and space them all out. But if I instead decide to keep 1 p orbital and put a lone pair in that p orbital, then what can happen with these adjacent p orbitals?
Like push the electrons around from one to the other.
Yeah, that delocalization, the spreading out of electrons, which we said is really stable. So if you are an oxygen, you have the choice to delocalize and spread out your electrons. 100% of the time, you're going to do that. So that's why this oxygen chooses to keep one of its p's as a pure p orbital and just hybridize the rest of them, so it can undergo delocalization here. Similarly, over here, the nitrogen. This nitrogen has 4 electron domains, so it appears to be sp3. It has a lone pair, and it's adjacent to a pi bond. So it's going to be sp2 hybridized, and we could think about drawing actually the resonance structure of what would come out of it. And here, it would look like a double bond over here, and then a single bond up here. So this is our major exception to the rule. Are we ready to try it out on one of the challenge problems? Okay. So I want you to take a second. This is on challenge problem 7 on page 45. And this is not the answer to the challenge problem, but you will need to do it to figure out the answer. So I want you to think about what are the hybridizations of this nitrogen and this oxygen. Think to yourself, try to work it out, and try to test out the neighbor rule. So for these two. We're still wrapping up if you thanks. So first off, does this nitrogen have any lone pairs on it? Yes, it does. How many electron domains does it have? 4. So it appears to be sp3 hybridized, yes? Great. It has a lone pair, we already said. Great. Is it adjacent to a pi bond or an empty p orbital? It is. So what's its hybridization? sp2. What about this oxygen over here? How many lone pairs does it have? 2. What's its electron geometry appear to be? Yeah, or hybridization I meant. sp3. Good. So, and then is it adjacent to a pi bond or empty p orbital? No. So this one's going to be sp3. Now I'm going to do one more further thing here, which is this lone pair here. If the nitrogen's sp2 hybridized, is the lone pair in a p orbital or in an sp2 orbital? P orbital, because that's the whole point of doing the neighbor rule and hybridizing, is to put its lone pair in the p orbital so it can spread out. So we'd say our lone pair is in a p orbital. And the very last one, and I'm going to go like a minute and a half over, so sorry, is these two nitrogens. So this bottom nitrogen, does it have a lone pair on it? It does. Top nitrogen does as well, because they both have 3 bonds. Now, how many electron domains does this nitrogen have? 3, right? It has 1, 2, 3. So what's its hybridization? sp2. So does neighbor rule apply? No, it has to appear sp3. So we just know that this nitrogen is sp2. And then this top nitrogen, does it appear to be sp3? Yeah. Does it have a lone pair? Yeah. And then, is it adjacent to a pi bond? It is. This is a neighbor. So we know that this is sp2 by neighbor rule. The last part is, what orbitals are these lone pairs in? Well, let's do the top one first. So the whole reason for the neighbor rule is to put the lone pair in a p orbital, right? So we know that. But then this bottom one, how do we know whether or not the lone pair is in a p orbital or an sp2 orbital? Any ideas? Daniel? For the neighbor rule, yes, 100%. The whole idea is the only reason we hybridize to be sp2 is to put this lone pair in a p orbital. But this wasn't the neighbor rule. This is just sp2 hybridized. So how do we know if our lone pair is in the p orbital or not? I'm going to go here.
I'm Dylan.
Dylan.
Since it's a pi bond and pi bond has to be in p orbitals and there's only one available p orbital,
Yes. So in our hybridization, if we're sp2 hybridized, we only have one p orbital, and then the rest are sp2. Because we have a pi bond here, we know that p orbital is part of that pi bond. So for this lone pair, do we have any available p orbitals left to use? Simply no. So we know that this lone pair is in an sp2 orbital, because that's all that's left. And that information, I know it seems like a lot of detail, but like that is what you need to think about to answer this. It's going to be a question about acidity and basicity that involves some lecture 2 stuff, but really good work on this. Thank you for letting me go a minute over. I will see you tomorrow, and then I'll stick around for some questions. Thanks for coming to section.